Hi folks, welcome back to my channel. I hope you guys are having a wonderful day. Okay, so today I will be teaching another sum based on LPP using graphical method. As you can see, this is the question. So from the question, similar way I am going to formulate. First, I'm going to find the equations, basically form the equation, and then I'm going to equate it using graphical method. Okay, let us start. What's the first line? X and Y are two products which requires the following capacity machines M1, M2, M3. Let's write it down. So X and Y are two products which requires the following capacity machines M1, M2 and M3. Okay, now see the next line. The next line says the available capacities are 50, 25 and 15. Available capacities mean the total capacity. In some other sum you can get it as the total units. So ultimately you need to understand that they are talking about the final value. Okay, so let's write these values: 50, 25 and 15. See, I've written 50, 25 and 15. Now let's see the next line. Product X requires 1 hour of machine M2, 1 hour of machine M3. And product Y requires 2 hours of machine M1, 2 hours of machine M2 and 1 hour of machine M3. So I'm going to write it. First one says product X requires 1 hour of machine M2 and 1 hour of machine M3. As you can see, the next one will be product Y requires 2 hours of machine M1, 2 of M2, 1 of M3. So this will be 2, 1 and 1. So when nothing is mentioned over here in the question, as you can see that product X does not require anything from M1. So automatically this will be 0. Now as you can see, this is kind of like the formation. Now let's proceed. The product contribution of the product X and Y are rupees 5 and rupees 6. So from the line itself, as you can understand, see, the above portion is already completed. Now my next portion will be forming the equation from this. So this portion is done. Now in LPP, the most important portion, objective function, is needed. So this will be the objective function, that is product contribution of the product X and Y are rupees 5 and rupees 4. So this will be my objective function. So let's write the objective function. This will be max z is equal to 5x plus 4y. Okay, so this is the objective function. Now let's write this one. So this will be x plus y less than equal to 50, less than because max is there. Okay, so let's write x plus y. Coefficient of x is 0, so no need to write this. Simply write y less than equal to 50. Y less than equal to 50. The next line will be x plus y will be equal to 25. I think I have done some mistake over here. The question says, for in case of y2, 2 hours of machine y1, yes, 2 hours of machine m2. So this will be 2. Sorry guys. Okay, so the next equation will be x plus 2y less than equal to 25, 2, because the coefficient is 2 over here. Okay, similarly the last equation will be x plus y less than equal to 15. Now for in case of LPP, the best way to write the equation or to complete the equation is, this is the objective function. Obviously, let me write it over here. You can get this as 1 mark question, like what this function is called. This is known as objective function. It is written this way: max z equal to 5x plus 4y. This is known as subject to this one. subject to. This is known as subject to. Okay, ST. So y less than equal to 50. Why I have used less than sign? Because it is max. For mean it should be greater than equal to. I have explained this in the previous video as well. This is a written rule you need to keep in mind, because if your signs are wrong, your entire sum will be wrong. You will get straight 0. So this is done. Finally, you end the equation by writing x plus y greater than equal to 0. Why greater? Because we are talking about product over here, isn't it? And product can never be negative. That is why you are writing greater than equal to. And xy, because obviously two variables are there, x and y. By the way, this is not called an equation. I am calling this an equation, but actually the name is constraint. So we have one constraint, two constraint, and we have another constraint. That is the third constraint. So in this equation we have three constraints, that is 1, 2, 3, and two variables x and y. Okay, now second step. First is, what you need to do is convert the inequalities into equality. Converting means, since the sign are all less than equal to, which matches the criteria of maximization. Okay, so you don't need to do any plus minus, simply make this equal. Let's do it. First equation is this one, y will be equal to 50. Second equation is this one, x plus 2y will be equal to 25. Third equation is this one, x plus y will be equal to 15. Okay, and max z will remain max z. You can write it, you don't have to write it once again, but just for your convenience I'm writing it once again. Okay, right, this is done. Now what I'm going to do is I'm going to create two rectangle boxes. Okay, so this becomes the final equation. So from here I have actually drawn two boxes. The reason why I have done two boxes, because obviously there are three constraints. I should have drawn three boxes, but the reason why I did not draw, because here the ultimate goal is, from one equation, from each equation basically I'm going to find x and y. So for this equation I don't need to equate it anymore, because already y is given, and when y is given x is not there. So automatically you have to understand that for the first equation, or the first constraint, for the first constraint x will be equal to 0. So x is 0, y is 50. So it's done. So no need to create any extra box. Now let's this is for equation number 2. I'm just writing it for your convenience. This is equation number 2 and this one is equation number 3. Okay, so let's see for the equation number second one. So the condition is, put one variable 0 and equate the other one. So first write x and y, since this are the only two variables used here. So when x, for this equation, that is equation number 2, when x equal to 0, y will be equal to 2y equal to 25. So y will be equal to 12.5. So when x equal to 0, y will be equal to 12.5. Similarly, do it for the opposite one. When y equal to 0, x will be 25. Done. For the third equation, this box is for the third equation. When x equal to 0, y will be 15. When y equal to 0, x will be 15, isn't it? Done. Now the next step is, I'm going to plot the graph. Okay, as you can see, I have plotted the graph. This is the x-axis and that is the y-axis. Now let's see the first value which I'm going to plot here. The first value is x equal to 0 and y equal to 50. Okay, so let's plot this in the graph. Okay, as you can see, x equal to 0, y equal to 50, x equal to 0, this is y equal to 50, means I need to plot it on the y-axis. So I have done it. Let's see the next two values. Now for equation 2 or constraint 2, the values are, when x equal to 0, y equal to 12.5, when y equals to 0, x equal to 25. So I'm going to plot this in the graph now. As you can see, I have plotted here. This is when this one is 12.5. So this one was when x equal to 0, y is 12.5, and this is when y equal to 0, x is 25. So I have plotted this. Now for the last constraint, let's plot the graph. So the last constraint is when x equal to 0, y equal to 15, when y equal to 0, x equal to 15. I'm going to plot this in the graph again. Okay, now I have plotted the graph. Now as you can see, my next step is to find the IBFS, that is initial basic feasible solution. We know that my question is based on maximization, which is less than equal to, isn't it? So for all the cases, I need to find the common region which has to be less than equal to these lines. Okay, so less than means downward. For this case, less than means downward. For this case, less than means downward. So I can choose this portion as the my common region, isn't it? So I can write this portion is known as IBFS. IBFS stands for initial basic feasible solution. Now, since this is the IBFS portion, find the coordinates. The coordinates are coordinates covering this. So this is 0, 0. This one is mine 15, 0. This portion I don't know right now. I'm going to find out. And this portion is known as 0, 12.5. Isn't it? So to equate this one, I need to solve equation number 2 and 3. By the way, guys, before going further, I've actually done one mistake. That is, this one was 2y less than equal to 50. So after equating, that would be definitely y equal to 25. So even in the plotting, it would have been different now. As you can see, I have plotted y equal to 25 over here. Now, what I was saying was to find this portion, that is this intersecting portion, I need to solve equation number 2 and 3. So this is how I'm going to do. So from these two equations, I need to find out x and y. So cut, this is y, this becomes 10. So when y equal to 10, I can write x plus 2y equal to 15. Sorry, this is 25, isn't it? Okay, x is 5. So the coordinate is 5 and 10. So let's write. Not getting any light. Yeah, there you go. X is 5, y is 10. I have chosen this one as well. So this one will be 0, 0. This one will be 15, 0. Let's write it down first. 0, 0. 15, 0. And this one will be 0, 12.5. What I'm going to do, these all are x, these all are y, isn't it? So now the objective function was 5x plus 4y. Let's go back first. As you can see here, the objective function is 5x plus 4y. What I'm going to do, I'm going to put those x and those y in this, and I'm going to equate it. So this is x, this is y, and this is the objective function. 5 into 5 plus 4 into 10. This becomes 65. This one is obviously 0. This one will be 15 into 5, that is 75. And this one is my 0 into 5 is 0. 12.5 into 4 is 50. Now the optimized value will be the highest one. Why highest one? Because I am finding max. If the question would have been in mean, minimization, then the optimized value would have been the least value among the 4. Okay, so but in this case, since this is a maximized one, so 75 is known as the optimized value, where x is equal to 15, y is equal to 0, this one. So this is the ultimate answer. Thank you for watching. Bye.